Hey guys, my name's Katie, and today I'm going to be starting this discussion by providing a brief overview on batteries, and then diving into a battery that's very prevalent in all of our lives right now, and that is the lithium-ion battery. We'll be discussing the chemistry behind how the battery works, its advantages and disadvantages, and then finally, its environmental impact and future role in sustainability. Batteries provide power to almost every aspect of our lives, from clocks to toys to Apple Watches and smartphones, and now even cars with the rise of electric vehicles. Batteries are able to do this by storing chemical energy and converting it to electricity. This energy is created through the flow of electrons from the anode to the cathode. Now let's jump into the chemistry behind how batteries work, starting with the three main components of batteries. As you may have expected, this process of creating energy requires chemical reactions. The first occurs between the negative anode and the electrolyte, resulting in the creation of electrons and positive ions. The negative electrons will then move to the positive cathode. This loss of electrons at the anode is an oxidation reaction. The second reaction occurs between the cathode and the electrolyte, giving it the ability to absorb said electrons given from the anode. When combined, the oxidation reaction at the anode and the reduction reaction at the cathode is known as a redox reaction. Every half reaction has its own redox potential, a value measured in voltage that determines the element's affinity to absorb electrons. The more positive the number is, the more likely that the element is to absorb electrons and become reduced. The opposite is true for very negative values, making the element more likely to give up electrons and become oxidized. On the screen now is a list of the redox potentials of some different half reactions. You'll be able to find a similar one in your textbook. The more different the redox potentials are of the two metals on the anode and the cathode, the faster that the electrons will move from the cathode to the anode. This increase in speed corresponds with a higher voltage battery and more energy being produced. So there are two main types of batteries: disposable ones that are also called primary batteries, and ones that can be recharged, which are known as secondary batteries. The main difference between these two is the ability for the redox reaction to be reversed. In rechargeable batteries, the anode and the cathode will do a kind of role reversal. When the battery is plugged into an external electrical source, the cathode will perform an oxidation reaction and send electrons to the anode where a reduction reaction will occur. This converts electrical energy back into chemical energy, letting the whole process repeat once more. While rechargeable batteries have a greater upfront cost than that of disposable ones, they are able to perform these charging and discharging cycles hundreds to thousands of times. Now, we're going to dive into a type of battery that was first introduced in 1912 by a chemist known as Gilbert Lewis, but whose technology did not become widespread until 1991. Lithium-ion batteries power tons of devices, including phones and many electric vehicles. You're probably even watching this video right now, thanks to the lithium-ion battery powering your computer. The reason that this battery is so popular today is primarily due to its high energy density, which means that it can produce lots of energy without being too heavy. This is due to the fact that lithium is the lightest as well as the most electropositive element. Lithium has a super low redox potential, a value of negative 3.05 volts, making it an excellent reducing agent and super willing to give up electrons. This high voltage and low weight is useful for many of today's technologies, as phones and other mobile devices are becoming lighter and less bulky. Let's take a look at how lithium-ion batteries actually function. Just like the typical battery, they have an anode and a cathode. As pure lithium is very reactive, it cannot be used on its own and must be combined with other substances. At the cathode, the reduction reaction that occurs is between a positive lithium ion and a cobalt oxide to create lithium cobalt oxide. At the anode, we see the oxidation reaction forming graphite, a lithium ion, and an electron. The full redox reaction is included on the slide. Because lithium-ion batteries are rechargeable, this reaction occurs both from left to right and vice versa. If read from right to left, then the battery is charging, and if read the other way, from left to right, the battery is discharging. Here I've created a table that goes over the pros and cons of lithium-ion batteries. Starting with the advantages, we have high energy density, which we've already discussed. Next, there's a low self-discharge rate. Self-discharge is something that occurs in all batteries. It is a chemical reaction that causes the battery to slightly discharge, even when not being used. This reduces the battery's ability to last its full charge duration. Batteries such as the nickel-cadmium lose roughly 20% of their charge after a month, while lithium-ion batteries lose only about 5%. Lithium-ion batteries are also a more eco-friendly option than their fossil fuel alternatives. While they certainly have their own environmental downfalls, as we'll discuss in later slides, the increased use of lithium-ion batteries in historically high greenhouse gas emitting sectors, such as the car industry, is certainly a big advantage. Lastly, lithium-ion batteries are low maintenance as they do not suffer from the memory effect. This happens when a battery is partially discharged and then recharged again. The battery will remember the most recent discharge and will stop working once it reaches that value, rather than reaching its actual full discharge. When this happens, the battery needs to be manually discharged, making the lithium-ion battery lower maintenance than some of its competitors. Despite the widespread use of lithium-ion batteries, there are some clear disadvantages. First off, lithium-ion batteries have an upfront cost that is roughly 40% higher than that of nickel-cadmium batteries. They also experience aging, something that many phone users are aware of. Most lithium-ion batteries only last for around 500 to 1,000 charging cycles before failing. The next disadvantage is one that I wasn't familiar with before this project, and is the flammability of lithium-ion batteries. When the battery charge reaches a level that is either too high or too low, some dangerous reactions can occur. The first is the formation of metal lithium at the anode, which can spark a flame when reacting with electrolyte. The other reaction is the production of oxygen gas at the cathode, which may be flammable when in high heat conditions. These potential dangers are certainly a disadvantage for lithium-ion batteries and cause some serious regulations for airplane transport. Finally, there is the risk that the lithium-ion battery experiences a deep discharge, which happens when it reaches a value of under 2 voltages. If it reaches this point, the battery can typically not recover. As far as the environment goes, lithium-ion batteries are pretty important. While Teslas aren't currently a common sight, by 2040, it's estimated that 57% of all vehicle sales will be electric. This is great news at a sustainability point of view, as cars powered by lithium-ion batteries tend to emit roughly half the emissions that a normal gas-powered car would. There is also the benefit that lithium-ion batteries can have on sustainability when paired with renewable energy sources, such as solar panels. These rechargeable batteries can store the excess solar energy acquired from solar panels and release it as electricity during periods without sunshine, or in periods without high winds with regard to wind turbines. Now let's discuss the environmental harm caused by lithium-ion batteries, namely the extraction of resources. Lithium is taken from salt flats via a form of mining known as water mining. This evaporation of salt requires lots of water. To put it into perspective, the largest lithium reserve in Chile uses 500,000 gallons of water to extract only 1 ton of lithium. Furthermore, the extraction of lithium requires the use of toxic chemicals, such as hydrochloric acid, that can end up in waterways and have been known to kill fish in a 150-mile radius of the spill. Cobalt, the element that reacts with lithium at the cathode, is almost solely found in the Democratic Republic of Congo. Its extraction has been known to cause some detrimental effects to both the land and the people mining it. Due to the close proximity of uranium, a radioactive element, to the cobalt deposits, as well as a lack of proper equipment given to workers who work in the mines, many children and men have experienced birth defects, lung disease, and miscarriages due to the toxicity. In conclusion, lithium-ion batteries are important to both our lives as far as technology goes, as well as from a sustainability point of view. With greater use of electric vehicles and more electric grids being built to store renewable energy, I believe that these batteries will continue to increase in prevalence. The effects of climate change worsening and a society becoming less dependent on fossil fuels will also have a positive impact on the growth of the lithium-ion battery industry. Currently, research is being done to find a solution to the environmental impacts of both lithium and cobalt extraction. One possible solution is battery recycling. If there exists greater access and advertising for lithium-ion battery recycling, then there will be less of a need to extract additional resources, making lithium-ion batteries even more sustainable. Well, that's it. Thank you guys so much for listening, and I hope that you are now more aware of the benefits, disadvantages, and power that batteries hold in our lives. See ya!